So here we go, guys. The fundamental theorem of calculus. Um, I put FTOC. Most textbooks probably just have it as FTC. And what this is saying here, let's see what it says. If f is continuous on a to b, then the function capital F of x from integral from lower limit a to upper limit x of f of t dt had the derivative at every point on x on a to b, and so the derivative of that function f of x, so there it is, that means derivative of capital F. So d dx, so I'm taking the derivative of this integrand, and it's saying that the derivative of that integrand is just whatever I have on the inside. That's what that proof is saying. Chav, I don't get it. We're about to do the proof of why this works. Here's the proof, by the way. There it is. I think, I guess if you're like super math savvy, you can probably figure out what they're trying to do in this proof. The expression in brackets in the last line is the average value of f from x to x plus h. We know from the mean value term for definite integrals that f being continuous takes an average value of at least once on the interval that, well, first of all, we haven't even talked about average value yet. But, and then they go to this, and then they go, oh, look, there it is. What happens to c as h goes to 0? As x plus h gets closer to x, it carries c along with it like a bead on a wire, forcing c to approach x. Since f is continuous, this means that f of c approaches f of x. Did anyone understand all that? No. Okay. We're going to do all this proof with pictures. I like how they do this. Look, they do all this here, putting it all together. This concludes the proof. We're about to do all that with pictures. So look, here, this is the big one. That's pretty much what the proof was trying to say. So, okay, I'm getting ahead of myself a little bit here. If the derivative of this integrand is itself, then if I erase the derivative, then that must mean antiderivative. But I am getting ahead of myself. We haven't done the proof yet, so we'll talk about it right now in a little bit. What's up? Integrand just usually means like whatever you have. You can use them interchangeably. This is an integral symbol, and then integrand is the property like yeah.
Okay, so the derivative of an integral is itself. So I was right.
What did you say last time? You said inverse?
No, I read it on my thing. Sorry. No, that's
yeah.
Okay, then I was thinking the whole time, I'm like, I think the second derivative of an integral is just f prime, right?
You're close.
No?
Oh, actually, no. Yeah, you're right. The second
derivative. It's just like a little trail.
Yeah. Well. Okay. But why? Yeah. So I think you got some points on that question.
Why? I think f prime is the second derivative of f prime. This is just like one line.
All right, check it out. Well, I'll say it like this: if the derivative, look, that's Woodlawn Lake. If the derivative of this integral is whatever I have on the inside, then that means if I delete the d dx, this must mean antiderivative.
So
Don't worry. Let's prove that this is true. What's up? Yeah, don't.
So they are inverse. Whatever makes sense. So it's like ln and e, like we just kind of get each other out, basically. Right. Okay, that makes sense.
But we're okay. Watch. Check it out. We'll go to the next page. It's blank on purpose. We're gonna draw. We're gonna do it in terms. This is probably the only guys. If after this proof you're still like, I don't get it at all. It's okay as long as you can apply it. It's like a definition. It's like a derivative rule. Just kind of like, remember how we did limits first and then we went right and transitioned right to derivative? I would like for you guys to know this, but is it detrimental? Is it like, oh my God, if I don't know this, I won't be able to do antiderivatives? No. You can still do antiderivatives just following the rules. Does that make sense? But I want you guys to know where it comes from. I'm going to go slow and then stop me if something doesn't make sense. Are we cool? All right, it says start with, so they call this capital F, and then I have a lower limit A and an upper limit X. So start by drawing a grid. I'm going to do the y-axis and the x-axis, and I'm going to draw a curve. So I'm going to go, here's my curve, and I'm going to call this curve f of t. So that's what they call it here at the moment. Are we still okay? Now, here's what we know so far. So I'm going to color code it. Capital F of x equals integral from a to x of f of t dt. So we know that this means area under the curve from x equals a. So I'm going to say a is like right here.
And it's like the same thing as n, right?
Yeah, A is just the lower limit, right? Okay, what was the question, Ms. Caesar? Yeah, A is the lower limit. If not, this means that I have infinite amount of rectangles, integral symbol.
Why are we equating? Where did T come from? Like, why are we equating f of x to f of t?
There, it says f of t here. They made remember it was a dummy variable. I can call it whatever I want.
But why is there a difference between the variables of like what's the difference between the variables of x and t? Because why is it f x is equal to the integral of f of t?
I need to have, this is a function. This is an integral defined as a function. So if I have an x here, if I put a 2 here, then I put a 2 up there. If I put a 3 there, then I put a 3 up there. We're not advanced yet, but this is an integral defined as a function. That's what this is. Integral defined as function. And they call that an integral capital F of x. That's what the author wanted to write.
So it doesn't matter the variable, it just matters.
It doesn't matter what this variable is. If I have an x there, then I better have an x on the top. I got to have an x somewhere. If I have and I guess technically you can have an x here as well, but it would be bad. I guess in physics they break that rule all the time. Yeah, this is a model in terms. This is a function in terms of x, so I better have an x in the upper limit. Integral is the area under the curve from a all the way to what? X. So I'm going to say that x is right here. So at the moment, this right here, that is your capital F of x at the moment.
You just putting it there just to put it like the x, like it could go anywhere.
Yeah, yeah, I just put it right there. Are we still okay? All right. So now I'm going to color code it. I'm going to get a different color. And let's see, what do I want to do? I want to do this. If this is capital F of x, because this is just an integral defined as a function, then I can do f of x plus h. I can put anything inside in there, right? Now, if I put x plus h for this one, then my upper limit where it has x, that's going to change to x plus h. So go a to x plus h of f of t dt. It's the same function. That's what the author wrote, just capital F. It's the same as saying y of x or any other letter. They just wrote capital F. We're still okay? All right, so this one in purple, if that's x, this says x plus h. So I'm going to say x plus h. I'm going to say that that is going to be like right here. So that is x plus h. So that means this area. Where that in what do you call that color? Violet. Where that is f of x plus h. What's up? Let's see. I just put it anywhere. I just know that it means area under the curve from a to x. Yeah, I'm just doing it based off of the definition that we know from what we know already. Ask me questions, guys. Are we all still okay with this? Okay. Oh, ask me, miss. Well, okay. Do you remember when all I'm doing it is based off of this? Integral from a to b of f of x dx. That was area under the curve from a to b of this curve. That's what we know. And we know that, right? That's all I'm doing. Look, I have a lower limit a. I have an upper limit x. So instead of b, I'm just going to call that x. And there it is. I'm just doing the properties. And they call that capital F of x. So all that area must be capital F of x. What happened, Cruz?
So f of t is the function, and capital F of x is the area.
Yes. Well, it's also a function defined in terms of x. It's a different function.
Okay, but
Capital
also
F.
the integral is also an antiderivative.
Well, that's what we're proving because we don't know that yet. We already know it. But we don't know that that integral means antiderivative until we do the proof.
Okay.
You know that because I told you it is.
Well, yeah, but so the only difference between f of x and f of t is the fact that f of t is the curve itself.
F of t is the curve.
F of x is the area.
Capital F of x is the area under that curve because it's defined as an integral.
Okay, that makes sense.
Okay. Nothing crazy.
So
Okay.
it would be like the same thing of saying like capital also be like g of x.
No, don't say capital F of t. That's different.
I mean, capital F of x. I could say like it's g of x.
G of if you want to call something, just what g of x is just something.
It's just variable.
Yeah, yeah.
Okay.
All right, are we still okay? Come on, Robasso, focus on this, miss. I need your A game on this because it is pretty important. All right, you guys ready? All right, so here's what I see. Let's see, what did they do on this proof here? All right, but I'm getting hints from the proof. See? So I see I'm going to take my capital F of x plus h, and I'm going to subtract capital F of x. I'm getting chopped. Why are you doing that? Well, I'm just following the proof. F of x plus h minus f of x. When I do that, do you agree that I'm going to have, if I do an LRAM, that I'm going to have this region right here? I should probably change the color. Let's do black. Because this is H right here. That gap, this gap right there, that's H. Do you guys see that? Yeah. All right, so that's going to give me, let's see, approximately, and then that's a rectangle, right? How do I find area of a rectangle? So that's going to give me H times, and then I'm using LRAM. That's f of x, right? I'm using the leftmost point, and how do I get the value of this vertical displacement? By plugging in that x to figure out what that height is. So h times f of x. Are we still okay? Okay, we're so close. Okay, are we okay so far? All right, here we go. You see this h times f of x? All right, come on, Rodriguez, focus. So I don't want approximate. Well, I guess first let's do what the proof does. I see that the proof divides by h. So you see this h right here? I'm going to go ahead and do what? Yeah, I'm dividing it. Chav, why are you dividing it? Well, the proof let me see that that's the direction they're going. But also because something's going to happen right here, something magical. F of x plus h minus f of x, equals f, well, not equals. Right now it's still approximate. Is approximate f of x. Are we still okay? Now, I don't want approximate. Let me come up to this picture. Do you agree that if I make a limit and I make h approach 0 or delta x approach 0 between x and x plus h is delta x. If I make this approach 0, won't that be right here perfectly at f of x? So there it is. So that's going to give me the exact. So here it is. I'm going to write limit as h approaches 0 of this stuff, f of x plus h minus f of x. This is capital F, not to be confused with little f, and that's going to give you exactly f of x. So catch up to here. Second. Oh, capital F is the integrally defined function. Capital F just is the integrally defined function. Are we still okay? All right, check this out. What do you observe? What do you remember about that? Does that not look familiar to you guys? That looks like the what? The definition of? No, it's not the alternate. This is the definition of what? That's the definition of derivative, guys.
I said that like 4 times.
It's the definition of derivative for capital F. Yay or nay? So what that means, so look how strong this means. This means F, capital F, notice that I'm drawing capital F with a little prime of X equals, and then what do I have on the right-hand side? F of X. So I'll slow down so we can see what all this means. I know. Okay, let's go back to what capital F was. Capital F, so look, we're so close, guys. Capital F of X was integral from A to X of F of t dt. Do you guys see that?
Because they're inverses, so whenever you take
when I take the derivative,
it's going to cancel out the integral, so it's just going to give you f of t.
There you go. Well, F of X. The t turns to X. Yeah. When I took the derivative, it just became F of X. Do you guys see that? Yeah. So now that we know, that's what they were trying to prove with all this mumbo jumbo right here. That's what they were trying to prove. I don't know if you can see it, but could you at least see it with the pictures? Did that help? So anytime, in conclusion, anytime we take the derivative of an integral, and so the bottom's a constant, the lower limit has to be a constant.
So
And
what's the difference of f, capital F of x and lowercase f of x?
well, lowercase f of x is usually for a function. That one, the capital F, they just said
So it'll be the same thing if it was like g prime of x is equal to f of x.
capital F, I can make that equal to anything as long as there's an x in it. So there's my integral, and I have an x on the top, so there it is. So capital F of x is just an integral defined as a function. Integral defined as a function. And then little f of t, little f of x, little f of whatever, that's just always just means function. It could be a polynomial, it could be a trig, it could be whatever. Okay, are we okay, guys? In conclusion, the derivative of this is going to be just f of x. Now, there is chain rule, and I'll write the chain rule in a little bit, but right now we're rookies, so we're just going to get accustomed to this. That's all we're doing right now. Notice it was a t. All that happened is I replaced with t with a x. Cool or not cool? F.
I wanted to write something else like in conclusion, anytime we take the
The derivative of an integral. You're just going to get the inside itself. But you have to have a lower limit that's a constant and an upper limit that has a variable. We're going to practice, guys. We're going to do a whole bunch of practice. So here it is. This is called the fundamental theorem of calculus. So if you want to give it a specific name, part 1. Part 2 means antiderivative. All right, here we go. Ready? Do I have an integral? Do I have a constant in the lower limit? Do I have a variable in the upper? Does it say d dx? So that means I'm taking the derivative of this integral. Are we okay? According to the fundamental theorem of calculus, this is equal to just cosine of x. Just cosine of x. Replace a t with an x. Bless you. Do you see what we did? There it is. I'm just using the rule, guys. We just did the proof right now, and all I'm doing is just using the proof that we just concluded. All right, here we go again. Do I have an integral? Is my lower limit a constant? Is my upper limit a variable x? Am I taking a derivative with respect to that same variable? Yes. Everything's being met. So my derivative of this integral is just 1 over 1 plus. Done. No, that would be the answer. No, that's it. No, that's the answer. I guess you can inverse of tan, and then you're taking the derivative of inverse of tan, and you're back in the same place. Do you see it? Yeah, Miss Ray here brought up a good point. Look at this, guys. Real quick, time out. Look at this. If I didn't have any of that information, what's the antiderivative of 1 over 1 plus t squared? No. This is arctan. What's the derivative of arctan? See? So do you see what's happening now? So we're just taking the derivative of whatever I have in there. Oh, okay, they cancel out. Boom. Do you see it? All right, here we go.
I thought you said we're chilling.
Yeah, we're chilling. We haven't done anything crazy. All right, this is chain rule. Relax. We're about to give you it's the same deal as always, guys. I'm going to be taking the derivative of this. Look, instead of capital F, they call it y now. Y equals this. So here is the chain rule. So with chain rule, so let me rewrite this. So I'm going to write d dx integral, and I'm going to put a as a constant. Yeah, hold on. Let me write the top. Instead of an x on the top, I'm going to write f of u. Is that okay with you guys? Okay. No, you guys don't like it. I saw your faces. I'm going to write u, where u is differentiable with respect to x. U is diff with respect to x. Hey, relax. We're okay. All right. We're good. All right, here we go. I'm taking the derivative with respect to x. So what's my first thing to do here? F of? No. F. What variable do I have up here? f of u, and then I got to go and do, well, that's not, is the u and x?
No, dudx.
Du dx. And then, of course, you replace that u with whatever.
So then it would be cosine x squared
Okay.
times 2x.
Yes, here we go. Y equals, yeah, you're getting ahead. Don't cook. Well, I want you to cook, but don't say it out loud so everyone else can cook. All right, y equals integral 1 to x squared of cosine t dt. You guys ready? Y prime equals, I'm taking the derivative with respect to, okay, I guess let me stop. Do I have a constant in my lower limit?
Yes.
Do I have a variable in my upper limit? Yes. Is it x? Oh, well, okay, yeah, it is x. Yeah, it's language play. It is x. Yeah, it is x. But is it quote unquote like x by itself, like just x? No, it's x squared. So because it's not just quote unquote x, I have to do chain rule. And it is on the top, so we're good. So I'm going to go cosine and then replace the t with whatever I have up here. What do I have? So that's what I'm going to type in here. X squared. Are you done? No. Chain rule. What's the derivative of x squared? 2x.
Why didn't we use one?
Why didn't we what?
Why did we use the upper limit, not the lower limit?
I did use the upper limit.
No, why?
Well, we had to. Remember when we did the proof?
No, I asked why did you use the upper limit, not the lower limit?
Oh, the lower limit has to be a constant. That's a property, miss, from when we did the proof. Don't worry, I see you, miss.
You just asked us if we want to put something else in.
Yeah, the lower limit has to be a constant. Yes, when we did this, look, the lower limits are constants. They have to be a constant. The lower limit has to be a constant. And then we did that minus this to get to here. The lower limit always has to be a constant. If it's not a constant, we can't use this rule.
But she's asking why is it constant?
No, I'm asking why we use like x squared and not 1.
Oh, we use whatever we have in the upper limits. See, look, that's x, so that's x. So here's my new rule in terms of chain rule.
So we just don't care about the lower limit?
We just don't care about the what?
Lower limit?
No, as long as the lower limit's a constant. We just did the proof right here of why the lower limit doesn't matter.
But the lower limit won't always be a constant?
Not always. Sometimes. Well, that's what we're about to find out right now. Okay, what's the question, miss?
So, it's not getting better, but if we're gonna have to start doing, I'm gonna start doing implicit, where it's like not with respect to x.
No, we're in Cal 1. It's not gonna. That's more for multivariable maybe, but I don't even remember them being in multivariable. I just remember doing like double and triple integrals with Bini's theorem, so you won't see them.
We had lines where we respect like u and we're doing x. Like we have.
Oh, if it's with respect to u, then everything's probably going to be in terms of u or something. There is something else, u substitution, but we're not there yet. Integration by parts and all that good stuff. All right, here we go, guys. All I'm doing is finding the derivative. You guys ready? I have an integral. Yes. Is my lower limit a constant? Is my upper limit a variable? But I noticed that, yeah, don't cook. You're cooking. Yeah. I want you to cook, but let everyone get the surprise as well. I have an upper limit as a constant and a lower limit as a variable. Do you know any properties that I can do to make is negate the right? Maybe, yeah. Negate usually means cancel, but I flip flop them, and then what do I put on the outside? So here it is. This is the same thing as y equals, put a negative on the outside, integral from 5 to x of 3t sine t dt. Is everyone open?
The negative outside of the limit.
Oh, as soon as I flip the limits, you put a negative on the outside because you're counting in reverse. Remember from
So because it's 3t sine t, it's not just 1, would we use chain rule? I mean, power rule?
it's just we're done. Does that variable, is that just x?
Yes.
Yeah, so we're just gonna substitute and that's it. I mean, I guess you could do chain rule. The derivative of x is 1 though.
Well, no, not chain rule, power rule. Because it'll be 1 squared.
No, remember this is an integral.
Oh, right.
So we only care about the number on the top of the box.
Yes. All right, here we go. Here we go. You're getting ahead of me, guys. A y prime equals, I have a constant on the bottom. I have a variable on the top. Leave that negative alone. Open parenthesis. All I'm going to do is replace a t with a 3x sine x. Close it. You're not doing the product rule or anything. If they were to ask you for a second derivative, then you would do product rule. But they're not asking for a second derivative. Leave it alone. Why don't we do what? Yeah, if they were asking for the second derivative, then we'd do a problem.
Okay, yeah.
What's up,
Why is
Miss?
3x sin x just considered the first derivative?
Because I'm taking the derivative of an integral with a lower limit of a constant and upper limit of a variable. And according to the fundamental theorem of calculus, that just means whatever the derivative of the expression in the inside of that integral is.
Like, first step of the derivative was just like taking out the negative and switching it.
Yeah, that's the first step. What's up? I might have said too many words there.
So this one also chain rule?
The one on the bottom? Yes, but we have to do a trick.
No, this one.
Which one?
The one we're doing.
No, that's it.
But why aren't you taking the derivative of the x?
The derivative of x is 1.
But the derivative of 3x is 3.
No, I'm not doing the derivative of 3x. I'm doing the derivative of the whatever you have up here. That's why I wanted to write. See, it says du dx, so take the derivative of that. You're not taking the derivative of f of t. You know what I mean?
Yeah.
Or are you just saying that?
Okay.
All right, look, some more, guys. Do I have a constant in the lower limit? There's a variable there. I do have a variable x in the upper limit, but I'm going to have to break this up. So here we go. You can choose your favorite number. I just like to go with the alphabet, but if you want to, do you guys want a number or a letter? A letter. I like to go in the alphabet. I just go A, B, C, D. So integral 2x, so that's where I start. So I'm going to stop at letter A. I'm going to call that a constant of 1 over 2 plus e to the t dt. Are we still okay? Where this one stops, the other one better starts. So plus integral, and my lower limit has to be the same as what it was on the upper limit on the previous integral. So a, and then I'm going to make the end limit, my upper limit be x squared. And I have, of course, the same expression. And of course, we couldn't do this before because we didn't know the properties, but now we do. Does that first line make sense to you? Okay.
Sorry, what did you put A on the bottom?
Where did I put what?
A on the bottom of the integral?
Where this one stops, the other one better begin.
Oh, okay.
All right, next. Do I have a constant on this, the lower limit of that integral? No, so how do I get the constant to be in the bottom and a variable to be in the top? I flip them and I put one on the front of the integral. A negative. So here it is. Y equals, put a negative, integral, lower limit a, upper limit 2x, 1 over 2 plus e to the t dt plus integral a, upper limit x squared, 1 over 2 plus e to the t dt.
It wouldn't be considered y prime.
Say it again.
It wouldn't be considered y prime.
I haven't taken a derivative yet. He still has integrals. What's up?
Never mind.
I haven't taken a derivative yet, guys. It still has integrals. You guys ready? Here we go. Now I'm taking a derivative. So now I write y prime equals negative. That negative is this negative. Parenthesis. Wherever I see a t, I'm going to write what? No, not 2x. 1 over 2 plus e to the 2x. We're not done yet. Chain rule. Times times 2. Does everyone know where that came from?
So can I just put the 2 on the top?
Yes. I'm going to rewrite it a little bit. Plus, say it again. That plus is this plus. Are we still okay? Do I have a constant in the lower limit? Do I have a variable at the upper limit? But notice it's x squared, not x. So I'm going to go 1 over 2 plus e to the what? X squared. Now chain rule times 2x. Are we still okay? And if you want to put all that in parentheses like that. All right, so here's my final answer. I'm going to write it right here nice and pretty. Y prime equals negative 2 over 2 plus e to the 2x. Make sure that negative is out. Well, I guess you can put it with the 2 if you wanted to there. Plus 2x over 2 plus e to the x squared. Does that make sense, guys? Okay. Here they are with their capital F's again. I'm not a big fan, but that's... sorry, dad joke. I thought about a big fan. All right, here we go. Look what this says. if f is continuous at every point a to b and f is any antiderivative of f on a to b, then the integral blah blah blah. This is part of the fundamental theorem. Okay, they don't even do a good job of explaining. All right, here's what they were trying, or maybe they do a good job, and I just see that, I just think that they didn't do a good job. What are they trying to tell me? They're trying to tell me this. Imagine this is not there. If the derivative of this is f of x, and I take away the derivative, then obviously this must be antiderivative upper minus lower. That's all it says. So, yeah. So what this is trying to say is this. Integral a to b of f prime of x dx. Do you see, does it say derivative? Does it say d dx on the outside? No. So that means I'm just doing f of x from a to b. That's how you say evaluate, which equals f of b upper minus lower. And don't worry, we're going to do a whole bunch of rules. This is considered fundamental theorem of calculus part 2. Say that again? Yeah, the dx goes away when you do antiderivative. But you got to have the differential there. What's up? No, I'm just rewriting what this is. That is this. Oh, that just says antiderivative. Antiderivative of x. So I just did this better. That right here is this. All right, guys. I don't want you guys to freak out. Look. This right here is this. I just wrote it better so we could understand it better. F prime, antiderivative of f prime is f, and I just did upper minus lower. Cool? All right, here we go. Yes?
Why is there a lowercase f in the integral and uppercase f?
That's why I told you that capital F is is f. It says right here, miss, capital F is an antiderivative. We're okay? I look, here it is. F this. Yeah, they just wrote it weird. Look, that's f prime. Antiderivative of f prime is f. I wrote it better. The authors probably think you guys are math majors and are reading everything. I don't know. So, am I making sense? Okay. See, I wrote it better so we can understand it better. All right, here we go. I wrote it again here. To put simpler, that's what they were trying to say. And we're gonna go pretty easily, I think. All right. All right, here we go. Ready? I have an upper limit of 3, a lower limit of -1. We're gonna go slow. Ready? Integral -1 to 3 x cubed plus 1 dx equals. What's antiderivative of x cubed? There it is. Plus, what's antiderivative of 1? X. Close it. Put a line like this. -1, 3. That means evaluate. Bless you. Are we still okay? All I'm doing now is upper minus lower. That's all I'm doing, guys. So I'm going to put equals. I'm going to do the 3 first. Open parenthesis. 3 to the 4th over 4 plus 3. Close it. That's the upper. That's f of 3. Minus, open parenthesis, -1 to the 4th over 4 plus -1. That's all I'm doing. That's it. Does that make sense? You're done with calculus. We're just doing arithmetic. What's up, Kyle? Yeah. You sure?
Yeah.
Okay. Let's see if we can do this. And if we need to use a calculator, that's fine. But let's see if we can do it without a calculator, because you're gonna have no calculators for the majority of it. 3 to the 4th power. Well, let's see. 3 times 3 is 9, and 9 times 9 is 81. Right. So 81 over 4 plus 3. We'll see if in a little bit we need to get a common denominator or not. Minus, open parenthesis, -1 to the 4th is going to be 1. So 1/4 minus 1. Are we still okay? All right, let's see. I'm going to distribute that negative. So I have 81 over 4 plus 3 minus 1/4 plus 1. All I did was, I know some of you are saying chop. You could have just done negative 3/4. That's fine. Whatever you think is easier. I'm just going with the flow here. Are we still okay? All right, here we go. 81 over 4 minus 1/4. That's going to give me 80 over 4. In a little bit, we'll reduce it. If you want to reduce it right now, that's fine. What is 3 plus 1? 4. 4 goes into 80 how many times? 20 times, no? What's 20 plus 4? 24. Okay, what do you guys think? We're going to do a whole bunch of those, so don't worry. And then the chop, I found this integral symbol in the calculator. Can I use it? That's what we were talking about last time. Do you guys have a calculator with you guys by chance? Okay, grab a calculator. You can also do this on Desmos. Wait, I don't know if Desmos. Oh, Desmos, I think will just give you the number. Oh, yeah, your calculator. It's this one right here. I made sure no one used this. That's why I put it right here. Because if not, someone would have used it last period. Grab one from that bag and then put it back. Because those are the Decathlon calculators. Those are the new ones. They're the nice ones. All right. Here we go. Let's learn how to use our calculators. Take your calculator out. Click on math and go to number 9. Does everyone's calculator look like this? Yeah, let's do it again. Math and number 9. Everyone's calculator look like this. What was my lower limit? Put negative 1. What was my upper limit? Put a 3. And my function was x cubed plus 1. So do this. The x is located right next to the alpha, so you don't have to push alpha x. You can just push x immediately. Does everyone have it looking like this? All right, now push enter, and you should be getting the same number that we just got. When you do your delta, when you do your UH quizzes, guys, please do it by hand initially. I'll let you guys know which ones you can use the calculator for, but 60% of your exam is with no calculator, and you better believe these are going to be in there without a calculator. Cool or not cool? Yeah, the only ones that, like, if you have a calculator with an integral that's super complicated, then you'll have a calculator for that one. All right, let's go to the next page. We're so close, guys. This is the last page. We're so close. This was if we would have gotten this before we took the simulation, we probably would have gotten some points on some of those integrals. Integrals define functions. All right, so look at this. Using the graph of f to analyze, this is the h of x is an integral defined function. That it's an integral and you have an upper limit of as a variable x. So if this was h of 3, then you would go from a to 3. If this was h of 5, then you go from a to 5.
That's how we know like we can work with it because it has a constant at the bottom and then a variable at the top.
Yep. All right. The graph of a continuous function f, so with domain 0 to 8, is shown to the right. So what graph do I have here? F of x. So put f of x. You can also call it f of t, but I see the variable for the x-axis is x, so you call it f of x. Are we okay so far? All right. Let h be the function defined by, so there it is. H of x is defined. It's an integrally defined function. Does anyone have any issues at the moment? Okay. Buenos Aires, you're good? Okay. Yeah. Sorry, miss. All right, here we go. Find h of 1. So I'm going to go h of 1 equals integral from a to 1 of f of t dt. Oh, yeah, a is a. Sorry, I was looking at this one in the top. They tell me right here what the a is. What's the a? 1. There we go. Yep. Why is it equal to 0, Miss Cruz? You don't move. 0. Put in there for good notes. You do not move, so you haven't moved. 0. Is everyone okay with that? Okay. Is h of 0 positive or negative? Justify your answer. I don't know. Let's see. H of 0 equals integral from 1 to 0 of f of t dt. Okay, I'll let you guys catch up. This means area of the curve. I start at and I end at. So I start at 1 and at 0. So let me zoom in. Area of the curve at the moment, if I go from 0 to 1 is positive, but am I going from 0 to 1? I'm going from, so because I'm going backwards, this is, there you go. And that's what I'm going to say. I'm going to say this, I'm going to write this is negative like that. So I'm going to write h of 0 is negative since f of t, or f of x, it doesn't matter. I already said f of t, is above the x-axis, semicolon, lower limit of integral is 1, is x equals 1, and upper limit is x equals 0, comma, hence h of x, or h of 0, hence h of 0 must be negative.
What does that say after x equals 0?
Must. So let's see. Since f of t is above the x-axis, lower limit of I should say since f of t is above the x-axis on 0 to 1, x-axis, and then put on 0 to 1, parentheses or brackets, doesn't matter. I put parentheses because right at 1 it's 0, and right at, but that's fine, not a big deal. Since h of 0 is negative, since f of t is above the x-axis on 0 to 1, lower limit of integral is x equals 1, and upper limit is x equals 0, hence h of 0 must be negative. You can put there one more sentence counting backwards or starting at 1 and ending at 0 or whatever. But yeah, I would. But I would actually. This is perfect language for me. For me, if I were a reader, I've been a reader many years. If I see this, oh yeah, f of t is positive, and you start at 1 and you end at 0. Okay, credit. Does that make sense to you guys? Okay. Let's go to the next one. Find the value of x for which h of x is a maximum. Love it. Put that the domain is between 0 less than x less than 6, 7, 8, less than 8. Open interval. Open interval. Because there is a discussion to say, actually there is no discussion on this one. So this one would have been perfect. All right. You guys ready? How do I find a max? How did I used to find a max? Whenever what is positive to negative? The function? F of x? Tell me specific language.
Because the f prime of h is f of x, whenever f of x is going to go to positive negative, that we can have a
You guys are all so close.
Whenever f of prime is above the x-axis.
Okay, now we're talking. Now we're talking. Guys, in the first semester, remember we talked about the derivative, that's all we talked about. Whenever the derivative of that function changes from what to what, then that function has a max. Okay, what function am I looking at right here? H of x. So I need to look where h prime of x changes from. Okay, so here's what you're going to write. I'm going to write h of x equals integral from 1 to x of f of t dt, semicolon. What is the derivative of h of x? H prime of x, right? H prime of x equals, what did Cruz say? It's just what? F of x. Do you guys see that?
So then h prime.
So this function right here, no, look, this function right here that you're looking at, this is the derivative of h. Do you guys see what we're talking about? So where does this right here, this function, h prime, which is f, where does that function change from positive to negative? At x equals 4. So that's the language you need. So here's the language. I'm going to write it in blue. I'm going to write h of x. So you got to be specific, guys. This is why I'm telling you, don't lose points. I can't give too much details. H of x has a max at x equals 4 since h prime of x, which equals f of x, changes from what to what? Positive to negative. And I know you already said x equals 4, but say it again. Positive to negative at x equals 4. Full credit right there.
Do we have to establish that? Oh, wait, for the next one.
All right, here we go. Find the value of x for which h of x has a minimum.
Oh, wait, repeat the question.
Oh, yeah. What's the question, fam? I mean, what's because you're Sophia also. She said Sophia. You got two Sophias.
For this one, is it the inverse of f of x equals h?
Say it again.
The inverse of f of x equals h?
No, the derivative of h of x is still f. But they want the minimum, right? So it's wherever this derivative changes from. Oh, then in the open interval, there's none. This is such a bad problem then. All right, switch it out for now. It does have a minimum. The minimum's at 8, Miss Cruz, in case you were wondering. But take it out for now. I'll delete it later. You're good. Find the x-coordinate of all points of inflection. Okay, you guys ready? Points of inflection. You can talk about the second derivative, but the derivative that I got h prime. It's probably best to talk about h prime. Let's first review, I guess. So side notes. What do you guys remember about points of inflection? Whenever what? Okay, yeah. So second derivative, where h prime prime changes signs. That's where I have a point of inflection on h. H prime prime changes signs, semicolon, point of inflection on h of x. If you're careful, you can still get credit for h prime prime, talk about where it changes signs. But the best answer, what graph do I have here? H prime. The best answer is to use h prime. So tell me, where does h of x have points of inflection? At 1, at 3, and at 6. That's where h prime prime changes signs. But I'm not going to say that because I have h prime. You know what I mean? So I'm going to talk about h prime. So I'm going to say that h prime changes from what to what? And vice versa. Do the first one first. What's the first one? Decreasing to increasing. So I'm going to write h of x has points of inflection at x equals 1, 3, and 6. And why? You know what? You don't have to put a period. Since these are the x locations, I guess you could have just said locations, where h prime of x changes from, and give the first one first, from what to what? No, not increasing to decreasing. It's from decreasing to increasing. And then I'm lazy, so I just say what? And vice versa. That's my habit. Most of you will have my habits. That's full credit right there. How do you feel? Did we do a lot? All right. Trying to think of what you should do first. Do the Delta Math to get experience first. I don't think I hit you with this just yet. And then I do have a paper copy, but I won't want it back until next week. On Monday or Tuesday when I see you guys.